In the last video, we introduced epsilon-delta definitions of limits. Now we're going to do a bit more digging into what they really are and their really hidden powers. Can you find the similarities between these three functions? I'll give you no time. I'll tell you right now. They don't have existent limits at certain points. Let me give an example. The limit as x approaches 6 of 1 over x minus 6 does not exist. We write dne. The limit as x goes to 0 of square root of x does not exist either. And finally, the limit as x goes to 0 of the natural log of x also doesn't exist. But they clearly have some values that they go to. For example, this function, 1 over x minus 6, goes to positive infinity from the right and negative infinity from the left. Root x clearly goes to 0 from the right, and log clearly goes to negative infinity as it goes to 0 from the right. This introduces the notion of one-sided limits. And the idea between one-sided limits is that it's just a limit as x approaches a value from one side. So what does that really mean? We're going to draw our graph for epsilon delta again, and here's a function that we just want to give an example of. Let's suppose that we have x equals c over here, and the limit L will just be over here. What we want is we want to find out a sort of bound from just one side. So let's say that our epsilon is here, and here's our epsilon as well. But we want to see what happens as x approaches c from the left. So let's see we have this sort of delta bound here. This would be an appropriate bound of delta because within this range, all the values of the function are within that value of, within epsilon of L, including from the top in this little sliver over here. All right, so let's review what the epsilon delta definition really says. It says for any epsilon that's positive, there's a value of delta, which we can think of distance as greater than 0, such that 0 is less than x minus c is less than delta, will imply that the function's distance from its limit is less than epsilon. Now, I brought up one-sided limits for a reason. So let me write down limit as x goes to some value c from the right, or c positive. Let's hope that this is not the grade you're going to look for in the class of f of x. And we're going to say it equals L. Now, what does that mean? Remember that delta has two directions it can be in because it's a distance, it's positive. Here is c plus delta, and this is delta to the right. And here is c minus delta, or delta to the left. So, if x is only really approaching c from the left, or from the negative actually, so I'm actually going to rewrite, I'm going to use the negative case first. So c negative, all right? So that means that the lowest bound we're looking for is c minus delta. That's the minimum value of x. So what does that mean? How do we express that in terms of epsilon delta? Well, in an inequality, remember that it's a distance, meaning that if you destroy these absolute value of bars, you can really say that negative delta is less than x minus c less than positive delta. And now, if you add c on all sides, you can see, pun intended, exactly what we mean on the graph. We have c minus delta is less than x is less than c plus delta. So x, when with delta, is within this range of c. And if we're approaching from the left or from the negative, we only care about the left-hand side, which means that when we actually do an epsilon delta proof, we just say x is greater than c minus delta. And if we're approaching from the right, so this side, we're only concerned with the maximum value being c plus delta, which means that x is less than c plus delta, which appears over here. So you can literally see intuitively that we have a left-hand side over here and a right-hand side for limits that are both encapsulated within our main epsilon delta definition. Now the key with that is that if the left-hand side and right-hand side limits as x goes to c are equal, then the limit is going to be that value and it exists. If there are two different values, for example, the limit as x goes to 0 of absolute value of x over x, as you can see, it's going to be 1 over here and negative 1 here, the limit does not exist. So that's how you set up the one-sided limit epsilon delta proofs. Now, what if we have a limit value that exists from one side, right? For example, this value, absolute value of x over x exists, it's 1. But then if we said that log is approaching negative infinity from the right, wouldn't that mean that the limit as x goes to 0 from the right of log of x have to equal negative infinity? Well, yes. And let's explain that using epsilon delta. Except for infinite limits, we need to tweak the definition a little bit. We say for infinite limits, right, which just means limit as x goes to c of f of x is equal to positive infinity or negative infinity. And we can say c positive or c negative or c regular. All right? For example, the function 1 over x squared, which looks like this, will approach positive infinity from both sides. All right, so let's play around with this. We say let m be greater than 0. Now, what is m? M is a vertical threshold, as we call it. What do I mean by that? Well, let me show you. We're going to choose a delta greater than 0 such that as long as x is a certain value delta away from that limit c, we can guarantee that the function f of x will always be greater than the threshold m. What does this mean? So let's take a look in this example of 1 over x squared, or let's just draw a new graph. All right, here's the graph, and here's 1 over x squared. Okay, let's say our threshold is m, right here. This is our value of m, y equals m. Now, is there a value of delta that can guarantee that the function 1 over x squared is always greater than m? Well, of course. This delta works here, for example. Here it corresponds like this. And now, at this value, the function is already greater than m. So essentially, we're still rewriting delta as a function of m that guarantees that our function is always going to be higher than m for any m that we choose. So m is going to be infinitely large, essentially, but the function at that point will be infinitely larger, which means it will go to positive infinity. So let's take an example that's blending two different concepts. Let's blend the one-sided limit concept and the infinite limit concept. So let's say we have the limit as x goes to 0 from the right of 1 over x equals positive infinity. Think about it. If you plug in 0.001 or really small positive numbers, you get bigger and bigger numbers. And of course, the graph of 1 over x also depicts that. So we're going to say let there be m greater than 0, and we're going to choose a delta greater than 0 such that as long as x is going to be less than 0 plus delta, we can guarantee that the function 1 over x will be greater than that value m. All right, so again, you know the drill at this point. What we want to do is we want to express the right-hand side in terms of the left-hand side. So if we take the inverse of this entire expression, we have to flip the inequality sign, so we get x is less than 1 over m. But look, x is less than delta, right? So if we choose delta to equal 1 over m, we can guarantee that for any m that the devil chooses or the friend chooses as the size of our target, that delta has to be 1 over m, and that'll always guarantee that we're greater than that value. All right? So now the actual proof, again, is really simple. We say suppose delta is equal to 1 over m. Then 0 plus 1 over m is greater than x, which means that x is less than 1 over m, and therefore x is greater than m. 1 over x is greater than m, which is what we wanted to show. So we're done. And as you can see, there's no absolute values and any bounds on the epsilon or m side. So in a way, infinite limits are very much easier to solve and prove than the finite limits. Okay, what would change for negative infinity? So let's say negative 1 over x, and that'll equal negative infinity. So what would we change in this case? Well, m at this point has to be an infinitely small or negative value, right? So for negative 1 over x, the graph is going to look like this. Okay, so now we should choose or let m be less than 0, right? Because it's going to be a negative. We still choose a delta greater than 0, though, because delta is a positive value, and since we're approaching from the right, we still have x is less than 0 plus delta. Except in this case, 1 over x has to be less than m. Remember, for any infinitely negative m, we have to choose a 1 over x that's smaller to beat that threshold. So then, you take the inverse, and you get x is greater than that 1 over m, right? And then you can just model it again. You can say m is greater than 1 over x. Or, yeah, sorry, you get x is greater than 1 over m. So, I hope you understand how this works in general. All right. How about the case where we have square root of x, right? That's a one-sided limit. So let's use that example here. So we're going to say limit as x goes to 0 from the positive of square root of x. Well, that's equal to 0, we just said. So how do we use epsilon delta to prove this? Well, we don't need m and n anymore. So let's take a look. We say let epsilon be greater than 0, and we're going to choose a delta greater than 0 such that 0 less than, well, x is less than, and we get c plus delta. That's going to imply, actually we don't need this side here because we're just looking at the right hand side, but now we have to add the absolute values back, right? We have root x minus 0 is less than epsilon. Okay, but look, our c is 0, so we can get rid of that, and so x is less than delta. And look, since the root of x is already positive, we don't need these absolute value bars. They're redundant. So we have root x is less than epsilon, which means that x is less than epsilon squared. Which means that if x is less than delta and x is less than epsilon squared, if we choose delta to be epsilon squared, which is our function of epsilon, we can guarantee that for any value of epsilon that our friend chooses as a target or the devil gives us, if we just square that value, we will already be within the bounds. It shows how slowly the square root grows. So take a look. If we have the square root looking like this, and somebody gives us the epsilon bound of, say, 1, or let's say 2 actually. So here's the limit. So here's 0, here's 2, and then here is negative 2, but we already know we don't need that. So then if we do delta 1, 2, 3, 4, look at that. We're already within epsilon. So then the proof is simple again. You're just saying, suppose delta is equal to epsilon squared, and then what you do is you just work your way backwards. You say that x is less than delta, right, which is less than epsilon squared, which means root x is less than epsilon. And that's redundant. You can just add the absolute value bars for formality, and you get absolute value of root x minus 0 is less than epsilon, and you're done. That's what you wanted to show, right? So now let's look at limits at infinity. What do I mean by this? Sometimes there are functions that when they trail off to infinity, so as x goes to infinity, they will have a convergent value. For example, arctan of x, the inverse tangent of x, is going to approach pi over 2 as x goes to positive infinity, and negative pi over 2 as x goes to negative infinity. So you express that as so. You'd say limit as x goes to positive infinity of the function arctan of x is going to be essentially equal to pi over 2. Now, how do you use epsilon delta definitions to actually show this? We're going to tweak something different. And we're not actually going to prove this because it's a bit difficult to prove, but we're going to say this. We have let epsilon be greater than 0. And then we're going to choose a value n, right, that's greater than 0, such that if x is greater than that threshold n, which is our horizontal threshold now, then that implies that the distance between our function and the limit will already be within epsilon. So on the graph here, we can see that as we have a threshold of n, so let's say over here, whenever x is greater than that value, we must already be within epsilon. So let's say our epsilon looks like this. So here's our actual limit of like pi over 4 or something, or of infinity. Here's our epsilon L plus epsilon. Here's L minus epsilon, and you can see it goes to power 2.